Hello, and this video is on lesson 6-2, graphs of inverse functions. This begins on page 93. Learning targets here are to use the composition of functions to determine if functions are inverses of each other, and to graph inverse functions and identify the symmetry. It begins by saying you can use the definition of inverse functions to show that two functions are inverses of each other. Example A. Use the definition of inverse functions to prove that f of x is equal to 2x minus 1 and f inverse of x equals x plus 4 divided by 2 are inverse functions. So remember these are the functions that we used in the previous lesson, 6-1, and the way we found the inverse function of f of x is by going through the 4 steps, which I will do really quick. We replace f of x with y, and then we interchange x and y, and we solve for y, which gives us, we add 4 to both sides, so we get y is equal to x plus 4 divided by 2. So these, and then finally we replace the y with f inverse of x equals x plus 4 over 2. So this would be the inverse of the f of x function, which is what we have here. But since, remember, in the definition of inverse functions, we have to show that f of f inverse of x does in fact equal x, and f inverse of f of x is going to equal x as well. If they both equal x, then we prove that the functions are inverses of each other. So let's go ahead and do that really quick. What we want to do is notice our inner function in the first one is going to be the f inverse of x. So what is f inverse of x equal to? Well, that's equal to x plus 4 divided by 2. And so we can go ahead and take this now. We're taking this and we're plugging it in for x in my f of x function. And so what does that look like? Oh, it's going to look like 2 times, I'm taking that and replacing it with x. So we have x plus 4 divided by 2 minus 4. There we go. Now what is going to simplify here? You don't want to distribute the 2. Let's make it easy for ourselves. So the 2 over 2 simplifies to just 1. And what we're going to have is x plus 4 minus 4, which is equal to x, which is what we want to get. Okay. Now, if this equals x, you may be tempted to say, well, yes, they are inverses of each other. But you want to find the other composition function. They both have to equal x. It's not sufficient that just one of them equals x. So let's go ahead and figure the next one out. F inverse of f of x. What is f of x equal to? Well, f of x is equal to 2x minus 4. And so this is what we want to find. We want to take our inner function, which in this case is 2x minus 4, and we want to plug it into for x of our f inverse function. And so this is going to replace x. How does that look like? Well, it's going to look like this. 2x minus 4 plus 4 divided by 2. Okay, so now, do we have to distribute anything outside the parentheses? Nope. So we can get rid of the parentheses. And we can go ahead and simplify. Negative 4 plus 4 becomes 0. So we just have 2x divided by 2. 2 over 2 becomes 1. And we have 1x, which is equal to x. And yes, f of f inverse of x equals x, and f inverse of f of x equals x. So we just proved, using the definition of inverse functions, that they are inverse. These two functions are inverses of each other. Let's continue on. You can use the relationship between the domain and range of a function and its inverse to graph the inverse of a function. If the ordered pair xy is a point on the graph of a given function, then the ordered pair yx is a point on the graph of its inverse. Okay, complete the table of values for f of x equals 3x minus 2. Use the values to graph the function on the coordinate axis below. Alright, so this is just going all the way back to our function cycle. From our equation, we can convert it into a table. Here are my inputs, and we just simply take our inputs and find what the outputs are going to be. So our input is negative 2. We take this negative 2 and we plug it in for x. 3 times negative 2 is negative 6 minus 2, which is negative 8. So here's my first ordered pair. From that ordered pair, I can put it into the graph, which is negative 2, negative 8, right there. We can continue doing this, and we can get more ordered pairs. Here we have 9 minus 2, which is 7, and then 12 minus 2, which is 10. 0, negative 2, which is right here, 3, and 7, which is right there. Alright, let me go ahead and create this line. Actually, let me start right there, right there. There's my line. This is going to be f of x equals 3x minus 2. Alright. Use the table in item 4 to make a table of the values of the inverse of f. Then graph the inverse on the same coordinate axis. So f of x is equal to 3x minus 2. So we have to find the inverse, which we already know using those 4 steps. We change f of x into y. We interchange x and y, so x equals 3y minus 2, and we just solve for y. So we need to add 2 to both sides, so we get x plus 2 equals 3y, and then we divide by 3. And so final thing we want to do is write f inverse of x is equal to x plus 2 divided by 3. So here, let's see here. Oh, did we need to find this? No, we actually didn't, because of this sentence right here. If xy, the ordered pair xy is a point on the graph of the function, so these are all your ordered pairs, negative 2, negative 8, 0, negative 2, 3, 7, and 4, 10. All of these are ordered pairs on my graph. Then it says that yx is a point on the graph of its inverse. So that means that to fill this table out, I can take, all I need to do is switch these, so we can have negative 8, negative 2, 0, negative 2, 0, 7, 3, and 10 for are going to be ordered pairs on my inverse function. And so that's what would go in this table. But since I wrote it here, I'll just keep it here because I want to graph these on my graph. So let's go ahead and look for negative 8, negative 2, which is right here, negative 2, 0, 7, 3, and then 10, 4. Wait, is 10, 4 correct? Let me check that out. 4, 12. 4 times 3 is 12. 12 minus 2 is 10. Okay. So 10, 4. Okay, I put this point wrong then. I forgot how to count apparently. So 7, 3, and then 10, 4. Alright, that looks better. So let me go ahead and graph the inverse function. We could have done this two ways. And the way we just did it here is obviously the simplest way. But the other way that I was going to do was to take this, find the inverse function, and then graph this. Just pick out some points. And notice we can pick out the points -8, -2, 7, and 10. -8, -2, 7, and 10. And when you plug these in to my function, -8 plus 2, which is -6. -6 divided by 3 is -2. And you notice either way you're going to get the same ordered pairs for the inverse. So -2, 0, 3, and 4. And you can confirm that. Let's do one more. Let's take -2, plug it in for x. -2 plus 2 is 0. 0 divided by 3 is 0. But isn't it easier to just basically take your table from your f of x, switch the values, and you get this, you get the ordered pairs for your inverse. Alright. Now take a look at this. And let's go ahead and take a look. Let's graph y equals x. Y equals x. Why do I want to graph that? Well, let's go ahead and put it on the graph. And take a look at that. When we went over the transformations a long time ago, let me just use this graph. Remember when we graphed the function f of x equals the absolute value of x? It's a V shape that looks like this. There we go, that's better. And when we graphed f of, let's say this was g of x is equal to negative the absolute value minus the absolute value of x, the graph was reflected over the x-axis. So the x-axis acted like a mirror. It was a reflection across the x-axis. Well, take a look at this right here. Is there some sort of reflection going on here between f of x and f inverse of x? It's not reflected across the y-axis. Well, it's not reflected across the x-axis because the graph, if it was, it would look something like this. Let me use a different color. If it's reflected across the x-axis, the graph would look something like this, which clearly it's not. If it was reflected across the y-axis, it would be looking something like this. But here's why we drew y equals x as a dotted line. Could you say that this f of x is being reflected across the y equals x? And notice at the point that they intersect, that's exactly where it crosses y equals x. And as you can see, this whole graph right here, when it's reflected across y equals x, it gives you this graph right here. That is exactly how an inverse function is always going to look like. It's always going to be reflected across the y equals x dotted line. Let's look at another example. First of all, we want to find the inverse of x minus 4. Well, this looks very easy. Go through the 4 steps. Y equals x minus 4, and then you want to interchange x and y, so we get x equals y minus 4. You solve for y, you add 4 to both sides, and so you get y is equal to x plus 4. So here's my inverse. My inverse is f inverse of x equals x plus 4. Graph f of x and its inverse, f inverse of x, on there and on the dotted line, and you want to graph the dotted line y equals x. So let me just graph the dotted line y equals x, and let's go ahead and graph y equals x minus 4, f of x. Well, that's very simple. You just use y equals mx plus b. You don't need a table for this. My y-intercept is going to be at -4, and my slope is going to be 1. Huh. Something weird here, but yeah. Okay. I can see what it's doing. Alright, there we go. There's my graph. Now let's graph the inverse. The inverse function, I'll use black here. So again, we can use y equals mx plus b. My y-intercept is at +4, and my slope is 1, so it's basically going evenly. Now take a look at that. Are these two functions exactly mirror images of each other across the y equals x line? Yes, it is. Can you see how they're perfect mirror images of each other? And so we have found how to find the inverse of a function by going through the 4 steps. We have found how to find the inverse by taking a look at the tables of the function, and all you have to do is simply switch yx to get the inverse. And now, to find the inverse of a function by just looking at its graph, you just simply have to reflect it over the y equals x dotted line. And so that is how you find. Those are the properties of inverse functions. Alright, thank you for watching.